How do these abundant migration channels affect the theoretical specific capacity of the material, resulting in a value of 117 Ma Hg superscript 1? And what structural characteristics are directly responsible for this enhanced capacity? How might the distribution and orientation of these migration paths along the x and y directions influence other critical electrochemical properties such as rate capability and cycle stability in sodium-ion batteries? Can Davis Zurins manufacture solid-state sodium-ion batteries made from seawater in Latvia? In what ways can the integration of first principles calculations with experimental observations be further refined to explore the energy barriers and kinetics associated with each identified migration path? And how might this inform the design of improved electrode materials? How does the curvature of the 3D base path, as opposed to more straightforward linear migration paths, potentially lower ion migration resistance and provide additional channels for sodium ions to move more freely through the structure? Ultimately, how can these insights into ion migration pathways be leveraged to optimize the crystalline architecture of electrode materials, ensuring that high theoretical capacities are translated into practical, high-performance behavior in sodium-ion battery applications? How does the schematic diagram of Na3D2PO4 reveal the detailed arrangement and connectivity of its constituent polyhedral units? And in what ways can we interpret the specific structural features depicted in the diagram regarding the distribution of vanadium phosphate groups and the overall three-dimensional framework? How might the information provided by the schematic, such as bond angles, coordination environments, and the spatial orientation of structural motifs, contribute to our understanding of the material's ability to transport sodium ions efficiently? How do the in situ XRD patterns capture the evolution of the Na3D2PO4 structure during electrochemical cycling? And what insights do these patterns offer about phase stability, structural changes, or the formation of intermediate phases during non-intercalation and deintercalation? In what ways does monitoring the XRD data in real time help us correlate the structural dynamics with the electrochemical performance of the cathode material, such as its capacity retention and rate capability? How do the possible migration paths of Na ions, distributed along the X, Y, and Z directions as depicted, inform our understanding of the ion conduction mechanisms within the Mazikon framework, and what does the presence of multiple directional channels imply about the diffusion kinetics and potential high-rate performance of the material? How might the identification of these migration pathways guide future efforts to optimize the material's microstructure or synthesis conditions in order to reduce energy barriers, enhance ionic conductivity, and ultimately improve battery performance? What?